Assalamu alaikum everyone. Welcome to our project presentation of EEE-416. Our project title is Visualizing Data Path for Different Data Processing Instructions of a Complete Single Cycle Processor. Our group is consisted of myself, 1906, 142, 145, 147, and 150. This is the outline slide of our presentation. Our purpose of the project is to achieve better understanding of the architecture of single cycle microprocessor studied in our theory course. The diagram of a single cycle processor is fitted in two LED matrices, and the control signals are shown in using the LEDs. And the diagram shows the fetch and execution cycle for different instructions. Data path of instructions are highlighted step by step using different color on LEDs. A single cycle processor is a microprocessor that carries out fetch cycle and execution cycle in a single clock cycle. A control unit and 5 main blocks are there. The first one is program counter, instruction memory, register file, arithmetic logic unit, and data memory. In the right side, we could see the block diagram. The data path for add instruction add R0, R1, R2 is shown in this slide. This is the design circuit diagram of our project, and this is the connection of hub 7.5 input to our ESP32 and to the 16x2 LED LCD module to the ESP32.
I'm ID 1906147. We have seen the data path for add instruction before. Single cycle processor executes the whole cycle within a single clock cycle. However, for better understanding, we have demonstrated the full instruction cycle in some steps. Here we will show the steps for add instruction. Firstly, the program counter indicates which line of the code should be executed next and sends the address of the line to instruction memory. Instruction memory decodes the line and extracts which instruction should be executed and sends the register addresses to the bus. For add instruction, bus sends the opcode funct and destination register address RD to control unit. Control unit generates the control signals based on the instruction. Firstly, the control unit sends 00 as reg source to enable the input lines coming from bus. Then the address of the source registers are sent to register file from multiplexers, and register file extracts the values inside the registers. Register file sends these values to ALU, but before that control unit sends 0 as ALU's SRC to activate the input coming from register file. ALU adds the values of two registers, and ALU control signal 00 is generated from control unit for add operation. Then sum, which is the result of ALU, is sent to the multiplexer, and control unit sends a 1 to the max selection bit. Finally, write enable is activated by control unit to write the sum in the destination register. The LCD display shows the instruction in assembly language during the whole cycle. So this is the overall data path for add instruction.
This is ID 145. Next, we'll see the novelty of our project. Our goal for this project was to design a device that would help undergraduate college students understand the data path of a single cycle processor for different instructions. Our project is unique. There are no available devices that help us visualize the data path for a single cycle processor in the market. We used two 64x64 LED matrix and coded the entire single cycle processor onto it. Then for different instructions such as add, move, store, register, and load register, we implemented our own code to visualize their data paths. We used existing libraries in Arduino, but the codes we constructed for all the different instructions are unique and are an original contribution. Now we'll see the design consideration we had to take to build our project. There were a multitude of aspects we had to take into consideration while designing our project. As previously mentioned, there were no such available devices that showcase the data path for a single cycle processor. Therefore, we did not have any template to base our project on. We decided to use two LED matrix to help visualize the data path. Single cycle processor consists of many different blocks such as instruction memory, control unit, register file, ALU, mux, extend, data memory. We provide them distinct shapes so the viewer can easily discriminate between all the different blocks. A LCD display would show the corresponding assembly language instruction corresponding to the data path shown on the LED matrix. There were some limitation of tools when we were building our project. Our project showcases the data path on the LED matrix and the corresponding assembly instruction on the LCD display. We wanted to connect both the LCD display and the LED matrix using only one ESP32, but trying to run both using a singular microcontroller produced erroneous results. Our first assumption was that the disturbance on data path shown on LED matrix while connecting both LCD and LED was because they both had to share SCL GPIO 22 of the ESP32. This was later debunked as the LED matrix showed no disturbances while both were connected if we didn't implement the code to display in the LCD. This problem was left unsolved, and we decided to use two different microcontrollers, one for the LCD and the other for the LED matrix. Now, assessing the impact of our project, the concept of a microarchitecture and the flow of a single cycle microarchitecture are sometimes difficult for undergraduate students to understand. It can occasionally become difficult to understand due to the multiple control signals and variety of data paths. Sometimes a deeper comprehension of the entire project requires more than just theoretical knowledge. Our project can easily be put into practice in different universities where they offer the course microprocessor and embedded system. This project will provide assistance to students learning how the single cycle processors work when covering this particular topic.
So for this project, we each contributed equally in our material acquisition and hardware setup, and also in the coding section of our project, where we each drew up the necessary LED mapping in order to draw our single cycle processor, and then to show the instructions being executed for the demonstration that we gave. We also contributed equally in displaying the assembly language instruction on the LCD panel. And for teamwork, we worked on the campus offline. We divided the required labor among us and cooperated in finishing up the project. This is the logbook of our project and our week-to-week update. So the GitHub link directs you to the code section of our project, and the YouTube link is given where we show the demonstration of our project. This is the cost analysis of our unit materials. You can see that the LED screen was by far the most expensive one. It was also the most difficult one to get. And this is our total cost analysis. This is our timeline of our project. So for future work, we would like to overcome one hurdle that we faced, which was we had to use two ESP32 boards in order to screen our LED matrix and our LCD matrix. So when we tried to implement this using one ESP32, the power drawn for the LCD screen was hampering the usual operation of the LED screen. There were also a few instructions missing in our project, for example, the shift operation, and we are only able to show our code in an infinite loop where the loop shows all the instructions one by one. So for the future, we would like to go over all these hurdles and also to create a user interface where the user could input an assembly instruction and the LED screen would show that instruction being executed on the single cycle processor. These are the references that we use. Thank you very much.